Right. Now we're going to have something completely different from the networking world. Glenn is going to talk to us about CWDM.
Okay. Mike's good? Yep. Excellent. This is entirely about hardware. There is no software in here at all. I think I mentioned Linux once. The reason I'm giving this presentation to you is because I'm a networking nerd and I deal with backbone networks. The cost of optical backbone network technology is falling. And the bottom edge of that, the really simple stuff of that, is dropped in price massively. To the extent that it's competitive with Ethernet switching, or a good complement to Ethernet switching. And so it's something that as system administrators, you should have in your toolbox so that you know when it's suitable to use. Now, because this is a telco technology, it's very much removed from what you might do from a it's much best at this point in time to put your AM radio electronics hat on, because there's pretty strong parallels with that very old technology. Okay, the stuff looks like an Ethernet switch. It's got lots of ports, and you can run a link to the other end, and there are lots of ports that pop out. The word we use for that in networking is called multiplexing. And as you way used to that in your Ethernet switch is what we call statistical multiplexing. You packetize it up, you wait for a gap in the traffic, you shove it in there, and you pray that it gets to the other end. Right? What we're on about is wavelength division multiplexing. That is that we give each connection its own frequency, and everyone can go concurrently, and it all pops out the other end because we've pre-allocated the bandwidth. It's very much like an AM radio where you have a frequency and we allocate different frequencies along that dial. Coarse means cheap. Right? We're talking systems of 8 or 16 channels of a gig each, and there are also 10 gig variants of this, but I'm trying to stick with the simple stuff. And that's pretty much all you need to know. Because it's cheap, there are features that are in our expensive kit that do not appear here. Right? And I'll go through them as we come to them. The most important of those is management. Right? When you install one of these systems, there is no visibility from any computer anywhere. Okay, so as I said, it's like an AM dial. We assign each signal shown here in different colours its own frequency. And if you were to light them all up simultaneously, this is the response curve of the fibre, it would look vaguely like that on some sort of spectrum display. Not that you can, the reason this is faked up rather than a copy of a spectrum display is this is quite a big bandwidth from red about here on upwards, and you just can't build them. So all these are faked up. This here is a higher area of high attenuation in older fibres called the water peak, and as you can see it takes out a range of the channels. We'll talk about that later. You may or may not have one of those older fibres. Okay, so what do we drive one of these links with? We drive it with an SFP. Now I assume that everyone is familiar with a GBIC or an SFP. Yeah, CWDM SFPs are slightly different, not that you can tell, they come in the same box. In that, on the previous diagram you saw how we output at different wavelengths. So there is one SFP per wavelength. This one is a 1470. Treat them with a bit of respect because, as we'll discuss, these are much, much more powerful than the SFPs you may have using on your campus network. Discussed in the very next paragraph. Sorry, I rewrote these slides at 4 AM. So you can see a campus network, you've got about 8 dB worth of power budget. That will do you some damage to your eye. But because we can't amplify coarse wave division multiplexing, i.e. it's cheap, so the bandwidth is too wide for an optical amplifier, we have to use these as powerfully as we can so that we send the strongest signal possible so that we needn't do any midpoint amplification. So these output 25 dB, which, you know, with a normal one you may or may not have an eyesight issue after you stare into it. With these ones you definitely will. And so you need to take a lot more care with CWDM systems than you might with the lasers that you normally have. Not that I'd suggest being free and easy with a normal laser either. So, yeah, we can pass these around. These are duds and don't work, so you may want to note the manufacturer. Just pass them up the back. Okay, those SFPs have a little EPROM in them. The idea is you jam the EPROM in it, and it's got the parameters of the SFP on it, and the operating system can read it, and we can actually get Linux to dump that. That is completely useless because of vendor bastardry. Basically what vendors have decided is so that you can't install your own SFP, they will checksum that EPROM, and then if you insert an SFP that isn't expected into that switch software, the switch software will say, oh, not our EPROM, sorry. Right, and of course they charge more for that. No, the camera's on, I won't tell you which vendor it is, got a third of their profit 1 year from overpriced SFPs. Large North American networking vendor, colour bluish. Now, so what are we going to do about that when we want to run different sorts of SFPs? We program our own EPROM and we do the programming so that the checksumming works out right. This brand here is Flecht Optics with an X. They're based in Germany and they're very good. And cheap. Even so, the bastardry still hurts us because we've had to fake up the EPROM parameters. So if I read the input signal, because these FFPs will tell you how much light they have coming in, I compare it to the range of input signals allowed, and it's out of range. I go, 10 minutes to go. Oh my lord. Well, okay. So what happens in the hood of one of these boxes that looks like an Ethernet switch? Basically, we combine and split light, and we do that by jamming fibres together, because why not? It works. And, as I said, we don't amplify. And we're not going to talk about how amplifiers work since we can't amplify and we only have 10 minutes. And the other thing we can't do is change frequency once we've allocated the frequency. In fact, if you can work out how to do that without turning it back into electrical and then retransmitting it, patent the idea and retire. Okay, so this is what a typical multiplexer looks like. He says, grabbing the tool. Doesn't work nearly as well as I'd hoped. So this is the main fibre link here, and these are each of the channels. This here is a 1 to 100 tap so that we can tell that we actually have power on this without unplugging this and interrupting all of these customers. You can see here, this one outputs into the brown coloured channel, this one into the orange coloured channel, and the colours don't match, but you get the idea. Okay, so it's really easy to share a link between two sites. We put one mux at one end, we put another mux at the other end, we put brown SFP in one, orange SFP, blue SFP, purple SFP, plug them up, matching SFPs in the other side, and we're finished. We're running 4 gigabits a second on this 8 big gig bearer here, right? We're using 4 of the channels, down to various machinery here. The nice thing about this is use anything that'll take an SFP. Building management systems, AV systems, television, IBM mainframes, right? So if you, PABXs, so oftentimes we have to go to a lot of work to munge this stuff into IP to get it to the other site because we think we can just carry IP and Ethernet frames. This gives you an alternative that you can have in your kit bag so that when somebody says, we want to put an Ethernet switch and a PABX down there, right, you can say, oh, well, we either have to put a voice over IP card into the PABX and pay extra licensing fees and stuff, or we can put in an E1 to single mode modem and run a CWDM system, right? I'm not saying one's better than the other, but I'm saying you have a design choice here, right? And that's all the message I want to get across today. One of the other advantages is that these links do not interact with each other. So unlike an Ethernet switch link, you don't have to worry about quals between the services, and you don't have to worry about a denial of service, say, on your data affecting your phone calls. Right, there is one other piece of networking gear before we're out of here. It's called an add-drop multiplexer. Basically what it lets us do is have a chain, like a chain of Ethernet switches, we can have a chain of add-drop multiplexers. And so we have the big multiplexer at the start, we drop off brown here, we drop off orange here, we drop off blue at this side. And that allows us, for example, to chain together a whole stack of, I don't know, branch offices, right? Now the advantage of this, as opposed to a chain of Ethernet switches, is if we have a failure at the first site of power, then the next two sites keep running, right? Now you probably still want to put Ethernet switching at these sites, but CWDM is a good complement to that Ethernet switching, right? Because it gets us resilience from power fade. Okay, oh, and of course we need to buy less fibre. And I've just dropped the slide. Okay, in that other diagram, just to make life really complicated, if we take a loop of fibre, we can drive each site from this side of the loop and from this side of the loop and build ourselves a redundant network. So that as well as resistance from power fade, we have resistance to backhoe fade. Right? And you can see that layout of the system here. I've only got 7 minutes probably, and this man will kick me off, so we'll keep pushing on. But that is in lots of ways a better alternative than doing the same thing with Ethernet switches and putting up the spanning tree. Okay, I wanted to talk a little bit about optical fibre. Okay, so some optical fibre has this water peak attenuation, and before you deploy your CWDM system, you need to find out what sort of fibre you have in the ground. And here's where record keeping for fibre systems is really important, right? When somebody installs a fibre system, they give you a stack of documentation, file that. Don't lose it, because in 10 years' time when you want to use that fibre for this sort of system, you can go, oh, how lucky, we bought the right sort of fibre. Note that. That's what you want to spend your money on. Okay. Yeah. Okay, the other thing is these systems have a power budget. As I said, they output from their SFP at extraordinarily high power, and they rock up at the SFP, depending on the distance, perhaps at enough power to damage the receiver in the SFP. So what we have are things called attenuators that we can use to reduce the power seen by the SFP, and they just plug into the receiver of the SFP. And when you want one, you can never find one, which is the golden rule with attenuators, actually, truth be told. You can see them here, and you can see this one in the receive channel of that fibre there. They go on the receive side of the fibre at each end, right? Up against the interface, partly because that makes maintenance easier. You can rip the fibre off, make sure that the expected level is correct, and then plug it back into the attenuator. The power budget calculation is really simple. You look at you take the documentation for the fibre and the test results for the fibre. You say, what's the worst case signal seen by the receiver? What's the best case signal seen by the receiver? And does that range fit in the receiver specs? If it's above the receiver specs, then we drop it using an attenuator. If it's below the receiver specs, then we go shopping for other SFPs. Okay, we've already talked about eye safety. The most important thing for eye safety is to keep the caps on the cables. The caps look like this. What you should do is put a bag in every rack, a Ziploc bag, and as you take the caps off, put them in that bag, so when you take the equipment back out, you've got the caps on hand to put them back on. Right? You do not leave fibre or equipment uncapped, and personally, when I see it, I just write out an OHES record these days. I can't be asked. People should get in trouble for it. It's exceptionally dangerous. Okay, as I said, we need a high standard of engineering work for these sort of systems. which is a bit unusual. If you're used to campus fibre, you just plug it in and you've got 12 dB of loss. Who cares if there's a bit of dirt? These systems, we use one of these, a Cleatops cleaner, to clean one end. We use one of these, a one-click cleaner, to clean the ferrule on the other end, so that it's all clean. I've shown you the visual fault finder. These are quite good for tracing fibres. So you plug them into one fibre and the light comes out the other. And if I had mine in hand, I'll show you how that worked. Oh, yep, I've got a photo just in case I did run out of time. Also handy are light meters. You can see here, this one here is just back-to-back on the fibre, and this one I think has 10 dB worth of attenuation. And they're quite good for saying, I've run up my fibre system, and you use them very much like a multimeter. This is the result I expect, am I seeing it? As I said, there are very strong parallels to basic electronics. But you can also have a light source so that you don't have to rely on the light from the SFP, so you can test the circuits before you even install the active equipment. As I said, we clean everything. I think the next photo takes a while to come up because it's a big one. We clean the ferrule with that one. And so, as I said, they're electrical systems, so we fault find like we do with electrical systems. What's the level of light I expect at this point? Measure it. Is it what I expect? All right. Then I hypothesize that the fault is blah. That means if I measure here, then, you know, I can confirm that theory. There's a couple of good tools for fault finding. Loopback cables are good. The very best tool is an OTDR, but that's 10 grand worth of kit. That's a step up. I suggest you pay a contractor to come in with one of those if you have a fault you can't find with one of those. Here you can see a fault here. I've installed a MUX here on the wrong frequency and it's not passing the frequency of light that I expected. So we fixed that. Alright. So very last slide. Why don't you want to do this? Having pushed the positives and saying it's something to have in your toolbox. It requires dark fibre, which you may not have access to. There is no operational visibility of this thing, apart from the DOM on the SFPs at either end. The knowledge you need is very much a knowledge of physical work, right? It's not a knowledge of programming, it's a knowledge of cabling, a knowledge of cleaning, a knowledge of, you know, it's a much more hands-on discipline. And the topology isn't great. So we're sharing point-to-point links in an age where everyone wants an Ethernet switch network. But as I said, something useful to have in your handbag so that, you know, you have another technology you can choose from when you're faced with interconnecting sites. Done. To the second.